67 since that's what everyone is asking me. The highest score was a 96. The rubric was set up to grade leniently, so I wouldn't have to do a lot of curve afterward. I'm not saying there won't be a curve. I'm just saying that's part of why the average was as high as it was. Okay. So the problem that we're going to work on today is from the homework. It's 11, 8, I think. No, 6. 6, yeah. And it involves this reaction. Okay, so this is acetone, makes ketene plus methane, or A goes to B plus C. And there's a split before the feed to the reactor, or a combination. And then you have a PFR that is 500 liters, or decimeter cubed, same thing. And the species A is fed to the reactor, and they label this for you 10 moles per minute. And then you have this other stream, which can be used to feed inerts, to the reactor. And then they label this as CA01. So we'll follow that notation. Anytime we're talking about this stream, we'll put 01 there. What else does it tell us? The pressure coming into the reactor of the feed is 2 atmospheres, and the inert is also fed at 2 atmospheres. The entrance temperature of both streams is 1100 Kelvin. Yes, this is from the 5th edition. It's in the homework. It's 11.6. And some additional information is given. K is equal to the exponent of 34.34 minus, where T is in Kelvin. CPA equal to 170 joules per mole Kelvin. CPB 90, and the heat capacity of stream C is, of species C is 80. And then delta H reaction at standard condition is 80,000 joules per mole. Any questions about the setup? Okay, so the first thing part A asks you to do is derive an expression for the concentration of this species, the concentration of A in this stream, relative to, I forget what exactly it says you can use.
Is it liquid? Gas?
No, this is gas. That's why it's telling you the pressure. So it says derive an expression for the inlet concentration to the reactor as a function of the inlet concentration of A and theta I. All right, so we're going to move through this part a little bit quickly just because this is just deriving an expression with algebra. This isn't doing anything that you guys can't do already. And I want to make sure that we have plenty of time when we're going to talk more about doing this problem in Excel and other problems like it. So CA0 of O1 is equal to the flow rate of A in that stream divided by the volumetric flow rate of that stream. The flow rate of A in that stream is also equal to the flow rate of A that was given. And the volumetric flow rate of that stream you can get by taking the total flow rate and dividing it by the total concentration of that stream. So the total flow rate of that stream is just this again, plus the flow of inert entering the reactor, which I can also write in terms of theta I as FA naught times 1 plus theta I. Right? And then the total concentration, how do I get that for a gas? Ideal gas law. So it's the initial, because remember, this is just the initial concentration. So you don't have to worry about the fact that it's non-isothermal. You don't have to worry about pressure drop. Just the initial pressure divided by R and the initial temperature. And so eventually, just through plug and chug, essentially you put this into here, you put the total flow rate expression into here, and then you make the substitution to get rid of the flow rate of A. But if you left that in, I wouldn't care because it's given. But you can substitute it out so that this is only a function of those two things. But you end up with one over 1 plus theta I. So as a quick gut check, if theta I is 0, that means there's no inerts flowing to the stream. So the concentration of A entering the reactor is the same as the feed concentration of A. And as theta I increases, the concentration of A decreases in the feed going to the reactor. So that should match what you expect. And that's part A. Part A is, like I said, is fairly straightforward. Part B is kind of long-winded. Should have printed this. Sketch the conversion and temperature profiles for the case when there are no inerts present. Using a dashed line, sketch the profiles with a moderate amount of inerts present. And then using a dotted line, I don't know why it's so important to him to tell you what lines to use. Sketch the profiles when a large amount of inerts are added. It says qualitative sketches are fine, but we're going to do it quantitatively. And then describe the similarities and differences between the curves. So first of all, is that a clear question? It wants to know, as you go along the bed of the reactor or along the volume, you get a profile, right? So this is volume, which you could also put down here length, if you took into account the cross-sectional area as constant. And so how does the conversion change as you go along the bed of the reactor? And how does the temperature change as you go along the bed of the reactor? So what might we expect before we sort of start? So what would we expect for temperature? We start at 1100. Is this an exothermic or an endothermic reaction? Louder. Endothermic, right? It's positive. Positive delta H. So the temperature is going to go up or down? Okay. So we know at least the direction of the temperature. What about conversion? Where does conversion start? 0, right? If I have no volume, I have no conversion, and it's going to increase. So obviously the temperature is going to decrease, the conversion is going to increase. What happens as you go to higher and higher conversions? Will the rate increase or decrease? Right, the rate decreases at higher conversions because the concentration of the reactants is getting smaller as you do more and more reaction. What happens to the temperature? It also decreases, which also decreases the rate. So this isn't like that exothermic reaction case that we talked about the other day where you have to balance the two competing effects, right? This is a case where as you go along the length of the reactor, the rate's going to be slowed down for two reasons. One, you're losing temperature, and two, you're losing concentration. What might you expect to happen when I have an inert present? What will the inert do in this system?
Slow it all down.
Slow it all down, why?
Reduces the concentration.
It reduces the inlet concentration, And of course, it's present throughout, so it's going to reduce the concentration throughout the entire reactor bed, which is going to slow the reactor down. What else might it do, though? Think about the chapter that we're in. Yeah.
Keep the temperature a little higher.
It's gonna mitigate some of the heat loss because I'm essentially putting something else in there that can lose temperature, right? So I'm putting in a sink of energy, or actually in this case really a source of energy, because its high temperature can help keep the reaction going a little bit longer. So yeah, you do have competing effects here. One is that it's going to decrease the drop in temperature. The temperature's still going to go down, it's just going to go down less rapidly. But it's also going to dilute the reactants. So which one of those wins out is the core of the question, right? Which one of those is going to win so that ultimately, am I going to get more or less conversion as I increase the amount of inert within the system? Okay, so I didn't prep anything in Excel because I kind of wanted to make the point that you don't need to. We're gonna, before I drop the screen and everything, we're gonna go ahead and put up the equations that are relevant for the problem, right? We're gonna do the necessary setup. And then we're gonna talk about how to solve it numerically using just the simplest but also easiest to remember method, which is the Euler method, and then we'll do an example of that in Excel. And just generally, this is a good problem to use Excel for, because it's going to ask you to change a lot of things as you're going. It wants to know what's the effect of no inert, a little inert, more inert, right? It's also going to ask you in part D, I think, to make the reaction now exothermic. Okay? So there's a lot of information that's asking you. Solving it by hand would take a really long time. All right, so B starts out by saying if there's no inert. So let's start with that assumption ourselves. And then we will leave the inert in there and see how it changes things.